All right. Good morning, everyone. Do you mind if I use the microphone, or do you think it's all right if I don't? I mean, I think the microphone is good because when I'm doing problems on the board, sometimes I talk at the board, and then I want to just make sure that everybody can hear me. Okay? Is that pretty good? All right. So I am recording again. I hope you guys really appreciate the recordings. I know a lot of students have told me that really helps a lot. So I will continue to do that. We are recording now. What I want to do first is just try out our top hat devices. So if you don't have it today, that's okay. This is just a trial run just to make sure that you kind of know how to use it. Okay, you can use either your computer or your phone, either way. And let's go ahead with this first question, if you are ready. All right, so the question is, what are the three major themes of physiology? Okay, and the way you're going to do this is you're actually going to, here's your code, 538176. Text 3115 and your response, either A, B, C, or D. 3115 and your response. So is the answer Homo sapiens, contraband, and using the force? Homeobox, controllers and fluxes and farce? Homeostasis, control systems and forces and flows? Or none of the above? What do you say? And yes, if you already have a problem set number 1, don't worry about coming up here and getting that. But if you need a group video project sheet, just come on up, grab it. Okay, so I can see at the bottom here we have about 27 students that have answered so far. We have about 55 in the class now. Had to bump up the max student number to 70. All right, how many need a little bit more time? A little bit more time. If you're quick, I'll let you answer. Just give me a thumbs up when you're ready. All you have to do is text, if you're using your phone, 3115 and your response, or use your computer and choose A, B, C, or D. Good? Thumbs up? Not yet. Not yet. All right, I'll just wait for a minute. What we're going to be doing today, right after this top hat question, is we're going to be getting into our video project groups, okay, so as I promised. So what I'd like you to do when you take a look at this sheet is, actually when you turn this in, I only need one sheet per group. So not everybody has to turn this in, okay? I'm going to have you name your group. You can come up with something very creative. Make sure you have everyone's first name and last name in your group. And then you're going to choose what kind of project you'd like to do. An educational video, physiology in the news, some kind of physiology advancement, a pathophysiological state, comparative physiology, or an animation. Okay, so your group can decide what kind of video project you'd like to do. And then I want you to rank your topic from 1 to 5. Most people get their top 3, so that's perfectly fine. And then I will assign the topic to you, and you'll come up with your final kind of idea of what you'd like to do for your project. Okay, your final topic. All right. Did you get your top hat question? Okay, so let's go ahead and close this one. And all right, good job, everyone. C is the correct answer. 100% of you got that right. So hopefully this is how you use top hat. Again, I'll be doing the top hat questions right at the top of the hour. Okay? All right, so with that, let's go ahead and get into your groups. You can just meet your neighbors. I'd rather you have a group of 3 to 5, okay? And just go ahead and discuss. I'll give you about 5 or 10 minutes to kind of figure all of this out. All right.
You want me to move over there?
Yeah. Yeah.
And if you have any questions, just raise your hand.
All right.
There you go.
Yeah.
Yeah. Does anyone else need a group video project sheet?
I have just like 5 hours. Yeah. I mean, I know things too, but I don't. That is
I don't mind any normal.
What's that? All right. Question, when you rank your topic 1 through 5, 1 is your top choice, just so you know.
So,
No, it's like
that's what I'm saying. I just can't. Can you run down Actually, no.
well, I was about to say that. Yeah. I remember like early I just going to Yeah. I was about to say. Well, we don't all Oh, I like that one.
All right, everyone. How many of you need a little more time? You feel like you want a little bit more time? I'll give you a couple more minutes so that you can keep discussing. This isn't due until Tuesday, by the way. Okay? Yeah. You don't have to turn it in today, actually. Have some time to think about it. All right, so on Tuesday, I do want you to turn in your first problem set and your group video project, okay? All right, well, since you have a little time, if you're okay if we kind of move on. I actually just wanted to point out a few things, okay? So first of all, as you're going through the semester, these are my goals for you. First of all, the reason why you're doing this is I want you to realize the dynamic and ongoing nature of physiology research, participate in meaningful communication of science, appreciate how our understanding of physiology has been and is being constructed, and then engage your peers in the process of science as it relates to physiology. Okay, so again, when you master a particular concept in physiology, this is where I really want you to expand on your knowledge, okay? All right, a couple of things that are important. Number one, I'm going to just point out, you are going to need to have one relevant journal article and review article. Okay, so you're going to have to dive into the literature. If you don't know how to use PubMed, there is a tutorial on how to find journal articles relevant to this project. So, and if you have any trouble, you can always come up and talk to me before or after class, okay? Any questions so far? I just want to point out that you will need to find a journal article and a review article to support your video project. You will have to kind of outline all of your references. You also need to include 3 quiz questions. Let's go to here. So after your video, I want you to have like a check your understanding, 3 quiz questions, and then the next slide can be the answers. Okay, it's just to help students kind of with the knowledge that you're passing on in that video. All right, and then finally, I just want to kind of roll out this rubric here at the very bottom. 10 points are going to be for scientific accuracy. Clarity of information presented is going to be 10 points. Creativity and engaging your audience is another 10 points. Making a clear connection to physiology and physiology research, another 10 points. And are the findings greatly significant and why? Okay, that's only 5 points, and then you'll have, that's 45 points total. Finally, you'll have a self-evaluation sheet where you're going to rate yourself and your members in the group, what roles they played in making this video. Remember, it's only 3 to 5 minutes, but there's a lot that goes into this project, okay? So don't take it for granted. I'll probably ask in a few weeks, have you found your journal article and review article? Do you know where you're going with this project, okay? So I'll check in periodically through the semester. Any questions so far? All right, so let's go ahead and move on. We got to get through diffusion of uncharged particles today. Again, we're going to continue on with the continuum perspective and the random walk today. And then I'll apply that to osmosis, which was really just an extension of diffusion. Okay, so a little bit of a review for everyone. Let me switch over here. So just, I gave you a formal definition of diffusion and diffusional equilibrium. We talked about, in this case, I'm not going to go through all of these slides, but in this case, oops, let me open this up for you. If you pretend these are glucose molecules that are relatively uncharged, think about them like billiard balls, okay? They're going to move in a straight line until they collide with each other, and they're going to redistribute themselves due to random thermal motion until they're pretty much equally spaced, and that's called diffusional equilibrium, okay? So I gave you the formal definitions here. Over time, you can actually see how the concentrations change. Time A here is this point in time at the very beginning. Time B over a period of time is this line right here. And time C is when you've actually reached diffusional equilibrium. This is right here. You can see that the concentration changes. It's actually an exponential function of time. Okay, so that's clear in this particular graph. I will have a computer simulation after we go through diffusion of charged particles, and you'll see this again. So keep this in mind. All right, so then we talked about, again, the continuum theory. It's actually a perspective, continuum perspective. You're thinking about these molecules, like billiard balls, moving about in a straight line until they actually go across the pore. Now, I call this a statistical force. So when I say concentration gradient or chemical force, it's also really a statistical force. Okay, I'm using those all synonymously because the probability that these molecules are going to collide with each other and move from high to low is greater than the probability that these molecules in the low concentration in that compartment, they're going to collide and go the opposite direction. So it's just about statistics. It's just about probabilities. There is a flux in both directions, a unidirectional flux, but the net flux will always go from high concentration to low concentration. So that's kind of our review. Here is Fick's law. And let me just go through this a little bit more carefully than I did last time. I just want to go through these statements here so that you can really understand what's happening. The unidirectional flux from outside to inside, that's what this is. This compartment here, O is outside. This one is inside. So if the unidirectional flux from outside to inside is proportional to the concentration outside, okay, and the unidirectional flux from inside to outside is proportional to the concentration inside, then we can write this statement below. The net flux is proportional to the concentration difference. Outside minus inside, okay? So to set this with an equal sign, we're going to have to use a proportionality constant, right? So we can write it this way now with an equal sign. Net flux is equal to that undefined proportionality constant, and then the concentration difference. Concentration outside minus concentration inside. So now defining this proportionality constant, now we can substitute that with the area of this membrane, right? If we turned it, 45 degrees, you would probably see like millimeter by millimeter. It's going to be an area. We've already defined the diffusion coefficient as Boltzmann's constant times temperature. This is just the thermal agitation over 6 pi radius times the viscosity. So this is where we left off last time. I just wanted to go through a more thorough job of Fick's law. And remember, on the exam, I'm not going to give you any numbers to actually solve for net flux. It's all going to be about relationships, okay? The negative sign, again, is because the net flux is always going to proceed from high concentration to low concentration. So here's that negative slope. Hence, this negative sign here, all right? So that means that negative sign is really about just directionality. I had a good question about that right after class on Tuesday, okay? All right, so with that, let's just practice for a minute. If you have your sheet here, let's just do the first problem. You can turn to your neighbor, that's perfectly fine. I'll give you just a couple of minutes because it should be easy at this point. I told you that how to think about this equation.
So anything on the top will be like directly related, while anything on the bottom is inversely.
All right, everybody. How many need a little more time? Okay, so what do you have for the first one? If you increase the viscosity, the thickness of the solvent, what's going to happen to net flux? Decrease, right? Okay, and again, net flux is actually in moles per second. I just wanted to add that as well, so it might help you kind of visualize this as well. What about decreased temperature of the solute? Decrease, that's right. Decreased concentration gradient. Decrease, yes. What about increased membrane thickness? That's also going to decrease. Now remember, when you increase the membrane thickness, you actually increase the probability of backscatter, right? The probability that it enters into the pore, bounces back out the same side. All right, increased radius of the solute. That's also going to decrease. And finally, increased surface area of diffusion. Increase, right? That's the only one that's increase. So perfect. Okay, maybe let's do the second one real quick too. What will happen to net flux in moles per second of an uncharged solute as the system approaches diffusional equilibrium? Now we're kind of putting two concepts together. You have to know what diffusional equilibrium is. And now what do you think? What will happen to the net flux of an uncharged solute as the system approaches diffusional equilibrium? Is that your answer, everyone? C, right? That is absolutely right, C. So as you approach diffusional equilibrium, I want you to think about it this way. The concentration gradient is going to diminish, right? So the net flux is actually going to approach zero, all right? Okay, perfect. So let's move on.